Generally speaking, there are three types of sounds. Infrasounds, noises that are below 20 Hz, meaning no humans can hear them. Acoustic sounds, ones that humans can hear, normally with a 20 to 20 kHz range. And ultrasounds, noises with frequencies higher than 20 kHz. This makes them much higher energy than other waves, meaning they can penetrate materials far deeper, making them perfect for medical imaging. Ultrasound imaging uses echolocation to make images similar to bats. This means that they bounce sounds off of objects and use the time it takes for them to bounce back to make a measure of the distance between them and the object. They bounce back due to acoustic impedance, or the absorption of sound when in different mediums. This is determined by this formula, where Z is the acoustic impedance, P is the pressure, C the velocity of sound, and S the surface area. However, while bats can naturally do this, humans have to use special machines called transducer probes. There are two basic types of ultrasound scanners. A scans, which use the attenuation or gradual decrease of intensity of a single beam of sound to determine the distance and density, and B scans, which use a 2D array to both determine density and produce images. Both work fairly simply, as they produce an ultrasound into the body, and when they hit a boundary between tissues, such as changing from fluid to soft tissue, they reflect back and are picked up by the probe. This probe is coupled to the patient by a special water-based gel, which allows the sound to pass through the skin without being disrupted, along with making the probe less likely to slide, which would produce worse quality images. They then use the speed of sound in tissue, 1,540 meters per second, to determine distance and intensity of echoes, based off of time and amplitude. But how do they use one single machine to both emit and collect sound waves? Well, this comes down to the piezoelectric effect, discovered by Pierre and Jacques Curie in 1880. The piezoelectric effect essentially describes how certain materials, when an electrical signal passes through them, produce a sound wave. These materials are ones that are non-conductive and highly polarized, with ultrasound machines normally using quartz. And when the electric current passes through them, they change shape rapidly, moving and grinding and producing high-frequency sound waves. However, the interesting thing about this effect is that it is reversible. This means that if sound waves hit it, it will produce an electric current proportional to the power of the sound wave. This allows ultrasound machines to both emit and collect sounds with the same module. The most common use of ultrasounds is the monitoring of the development of the fetus during pregnancy, as ultrasounds are purely mechanical, meaning they don't produce any harmful radiation. This type of energy is known as non-ionizing, meaning it doesn't have the ability to remove electrons from atoms. This monitoring of the fetus means that doctors can identify potential problems, leading to many more healthy births. Additionally, ultrasound imaging is most common for pregnancies because it is very effective on soft tissue. Ultrasound imaging can also be used for brain scans, helping to determine how healthy it is without harming the brain. Another helpful medical application of ultrasound imaging is that it can be used to measure blood flow using the Doppler effect, in a process called a Doppler sonography. Doppler sonographies use the frequency shift over a particular area to determine the speed and direction of blood flow, allowing for the monitoring of blocked arteries or similar medical problems. The frequency of these sound waves changes because their reflection is changed when they bounce off of a moving object. If the object is moving away, the sound wave will decrease in frequency, while if the object is moving towards the recorder, it will increase in frequency. This allows the doctor to determine the direction of blood flow, and the specific frequency change is used to determine the speed of the blood. Ultrasounds also have therapeutic applications, which was actually their original purpose. The ultrasounds bring heat into the body in a localized way, which can be used to help treat many athletic injuries, such as sprained ankles. It can also be used to help treat cysts, and extremely focused ultrasounds can physically destroy kidney stones, allowing them to be passed without surgery. The main benefit of an ultrasound versus any other type of imaging is that it is non-ionizing, painless, and doesn't require much setup or needles. It is also better at capturing images of soft tissue than any other form of imaging, and can penetrate deep into the body, although those images would have a low resolution. Additionally, the process is not very expensive, on account of it being fairly fast and not requiring extremely expensive equipment. Moreover, it offers real-time imaging, meaning that experienced practitioners can diagnose on the spot, allowing patients to get treatment faster. Ultrasounds have some downsides, though. One problem is that they have the slight potential to heat tissue, creating potential pockets of gas that can be extremely dangerous. While this is extremely uncommon, it has happened on rare occasion. Additionally, because it is sound, it cannot get through pockets of gas, as it slows down too much, meaning that it is bad at imaging the stomachs or digestive systems of people with bloating problems. Finally, it is also difficult to use, as the probe has to be held perpendicular to the place that would be imaged, or it would produce abnormal variations in the image due to abnormal reflections. While ultrasounds are very useful in the current day and age, they haven't always been this useful. They've had to go through many stages of development, taking over 100 years to be created. Not only that, but there are still many places for the ultrasound to go. Here is a quick history of the ultrasound. With that, we come to the current day technology, a wonder of modern science, taking inspiration from across many disciplines, whether it be biologists and their experiments on bats, engineers designing the machines, doctors finding medical applications, or physicists discovering the theory behind it. The ultrasound is truly a great machine, and despite its flaws, something that will be used for years to come.